Here, I will explain the concept related to successive approximation analog to digital converter. Successive approximation analog to digital converter. Block diagram. Heart of the success approximation analog to digital converter is SAR, successive approximation register. Here Q0, Q3, Q7. This one is 8-bit SAR. 1, Q0, Q1, Q2, Q3, Q4, Q5, Q6, and Q7. One more block is there here. That is DAC, 8-bit DAC. 8-bit digital to analog converter. The output of the digital to analog converter is VA. This one is a comparator. Comparator output is given to that SAR. The data is entered serially into SAR from the comparator. This is D, negative and positive, inverting terminal and non-inverting terminal. This one is V, analog input. Analog input. But unknown analog input is compared to this DAC. Output of the DAC, that is VA. These are the bits B0 to B7. Serial data out. Serial data out. For the startup conversion, we use this one. For the startup conversion, SAR hold the signal as high, that is start is high. This is S. Complete conversion, this is complete conversion. Complete conversion. These two are connected. Startup conversion and complete conversion. Here apply some clock signal. Clock time is T here. This one is 8-bit latch. 8-bit latch. This one is latch enabled. 8-bit latch stores the 8 bits. This is the output. 3, 4 up to 8. Digital data output. Data output. Connections are like that. 3, 4, 5, 6, 7, and last one more is 8. This is the block diagram of successive approximation analog digital converter. First point here is The heart of the circuit is an 8-bit successive approximation register. This one is 8-bit successive approximation register SAR, whose output is applied to an 8-bit digital converter. 8-bit digital to analog converter. The SAR is from Q0 to Q7. That output is applied to an 8-bit digital to analog converter. The heart of the circuit, the heart of the above circuit is an 8-bit successive approximation register SAR, whose output is applied to an 8-bit converter, 8-bit digital to analog converter, whose output is applied to an 8-bit digital to analog converter. This is the heart of the circuit is SAR, successive approximation register, means 8-bit SAR. The output of the SAR is given to 8-bit digital to analog converter shown in figure. This is the analog output VA of the digital to analog converter is then compared to analog input signal VN by the comparator. This one is comparator. Second point here is the analog output VA, conversion output. The analog output VA of the digital to analog converter is then compared to an analog input signal, an analog input signal VA by the comparator. The output of the comparator is serial data to the SAR. The output of the comparator is the serial data input to the SAR. Next, comparator function is compare two voltages. First one is V in, analog input voltage. VA is the conversion analog output of the digital to analog converter, or a digital equivalent. VA is the digital equivalent of that DAC. Both VA and VIN are compared by the comparator circuit. The output of the comparator is a serial data that is input to the SAR. The main function of SAR is adjust its digital output. That means 8 bits. Adjust its digital output. Later we will see, until it is equivalent to analog input. Third important point here is the SAR, successive approximation register, then adjusts its digital output. That means 8 bits that is Q7 to Q0. Adjust its digital output until it is equivalent to analog input. Equivalent to analog input. That is later we will see with one example. Next, fourth point here is the 8-bit latch at the end of conversion holds onto the resultant digital data output. This is the 8-bit latch, which is used to store the output digital data at the end of the conversion. Digital data, V input to digital data. Fourth point here is the 8-bit latch, the 8-bit latch at the end of conversion. At the end of conversion, holds onto the resultant digital data. Resultant digital data output. The 8-bit latch is used to store the digital data output after the conversion. Conversion means V into digital data output. Next important point. The SAR is reset by holding the start signal high. One more here, start signal is there at the start of conversion. That means V into digital data output at the start of a conversion cycle. The SAR is reset. Reset means for all the bits Q0 to Q7, all are reset to 0 by holding the start signal. By holding the start signal, that means yes. The start signal is fifth point. At the start of conversion cycle. At the start of conversion cycle, the SAR, successive approximation register, is reset by holding the start signal, holding the start signal, that is S. Start signal S is high. SAR at the start of conversion cycle, the SAR is reset by holding the start. This is the start signal high. And the first clock pulse, this is the first clock pulse. Low to high, this one is low to high transition. The most significant bit output Q7 of the SAR is set. In this by using this at the start of conversion cycle, the SAR is set by holding the start signal. S is high because all the 0, 1, 5, 6, 7, 8. This one is Q7. This one is Q0. All are zeros. On the first clock pulse, low to high. That means first clock pulse means low to high transition. The most significant bit output bit Q7 of the SAR is set. This is the MSB. This one is LS. On the first clock pulse, low to high, and the first clock pulse, low to high transition, low to high transition. The most significant bit output bit, the most significant bit output, that is Q7 of the SAR is set. That means here MSB is 1. The remaining all are zeros. 1, 2, 3, 5, 6, 7, 8, 6. This one is MSB. This one is LSB. And the first clock pulse, high transition, the most significant bit output Q7 of the SAR is set. The digital to analog converter then generates an analog equivalent to that above digital data, which is compared with the analog input. 7th point is convert this data into digital decimal equivalent or analog. This 100, this 8-bit data is applied to DAC. 1, 2, 4, 5, 6, 7, 8. This data is applied to digital to analog converter. The output of the digital to analog converter is find out the analog equivalent. Find out the analog equivalent. That means convert this data into decimal number. That is the analog equivalent. Okay. The digital to analog converter, then generates an analog, equivalent to the analog equivalent of the data, the digital data like that. Digital data which is compared with compared with the analog input V in by the comparator. Okay. This VA is 170 is compared with VN by using that comparator. Check the conditions. If VN is greater than VA, if the comparator output is high, suppose comparator output, next point is 8th point is the comparator is high, if the comparator output is high, that is V in is greater than VA, output of the digital to analog converter. The most significant bit will stay as it is, and the next bit will and the next bit will be set, that is Q6 set for a new conversion, or comparison, for a new comparison. This is the comparator. Vin is given to this one. Here Vin, an inverting terminal. This one is output of the DA, digital to analog converter, VA. If Vin is greater than VA means Vin is connected to positive. That means Vin is more positive than VA. The comparator output is high. If Vin is greater than VA, the most significant bit will stay as it is. Already here Q7 is 1. The remaining all are zeros. Q7 is 1. And the next bit Q6 is also 1. The next bit is the Q6 will be set. That means 1. For a new comparison. The remaining bits are here. The remaining Q5 to Q0 all are zeros, like that. All are zeros. If Vn is greater than Va. Okay, next, 9th one. If the comparator output is low, if the comparator output is low, that is VA is greater than Vn. VA is greater than Vn. The most significant bit, bit is set to 0. The most significant bit is set to 0, and the next bit will set to 1. And next bit will set to 1 for a new comparison. This is the comparator. This one is VA. VA is greater than Vn means VA is connected to inverting terminal of the op-amp. That means high value, negative value. Vn is connected to non-inverting terminal. Therefore, output of the comparator is set to 0. At this condition, Q7, Q6. Consider these two, present bit and the next bit. Q7 is set to 0, and next bit is Q6. Q6 will set to 1. The remaining Q5 to Q0 all are zeros. Next one, in any case, either 8th point or 9th point, on the next clock pulse, low to high, the SAR will set the next MSB Q6. In any case, in any case, that means on the next clock pulse, low to on the next clock pulse, low to high transition, the SAR will set the next most significant bit Q6. In either case, in any case means this one Vin is greater than VR, VA is greater than Vin. The Q6 bit is set to 1. The Q6 bit is set to 1. But Q say in that case, Vin is greater than VA. The output of the comparator is 1. Q7 is 1. If VA is greater than Vin, the output of the comparator is 0. Q7 is 0. In any case, that means 8th point or 9th point. And the next clock cycle, second clock low to high transition, the SAR will set the next MSB Q6. Next MSB Q6 means either 8th point case or 9th point case. The Q6 is 1. Depending on the output of the comparator, the SAR successive approximation register will then either keep or reset the bit Q6. 11th point, depending on the output of the comparator. Depending on the output of the comparator, the SAR will then either keep or reset the bit Q6. Q6 is depending on the output of the comparator, the SAR will then either keep or reset the bit Q6. Again, conversion starts from Q6 to Q7 is completed. For that Q7, the next bit is Q6. For the next conversion, Q6 is the MSB. The next bit is Q5, like that. In that fashion, I have to cover all the bits. This process is continuous until the SAR tries all the bits. This process is continued. This process is continued until the SAR tries all the bits. That means in this example, Q7 to Q0. The LSB is Q0. As soon as the LSB Q0 is tried, SAR forces the conversion complete signal high to indicate that the parallel output lines contains valid data. As soon as the LSB, least significant bit, that is Q0, is tried, the SAR forces the conversion. The SAR forces the conversion complete signal. Complete signal CC. CC is CC high to indicate that the parallel output lines contains, to indicate that the parallel output lines contains valid data. The parallel output lines contains valid data. This is the at the beginning of the conversion, the start signal is high. At the end of that conversion, CC conversion complete signal is high. Conversion complete signal is high. After that, the parallel output lines, these are the parallel output lines, contain some valid data. The CC signal is turn enables. This is the complete conversion. Turns enables the latch. This is the latch. My connection is there here. Enables the latch, and the digital data appears at the output of the latch. And the digital data is, this is the digital data appears at the output of the latch. Digital data are also available. See, this is the digital data is also available serially, as the SAR determines each bit. Serially means one bit, bit by bit is appeared here. These are the parallel bits, parallel lines here. Next point here is 12th point. The CC signal, that means conversion rate. The CC signal is enables the latch, and digital data appears at the output of the latch, Digital data also available serially, as the SAR determines each bit, as the SAR determines each bit. The SAR determines each bit. To cycle the converter continuously, the CC signal may be connected to start conversion input. This is for in one V in comparison is completed. Some value is there. Hold value is there. Sample, and here some sample and hold circuit, some analog value. Hold value. This value is some 63, 123 is like that. Vin is like that. Vin is some analog value. Okay. The cycle the converter continuously. First hold value is converted into digital data. Next, second hold value. These are the hold values. To cycle the converter continuously, the CC signal may be connected to start conversion input. This is the CC signal is connected to start conversion. That means after complete the conversion, due to this connection, again new procedure will start, converts the next hold value into digital data. Next point is to cycle the converter. To cycle the converter continuously, the conversion complete, the signal, the CC signal maybe be connected to start, be connected to start conversion, start conversion input. Next, the time for one analog to digital conversion, that one hold value, one analog to digital conversion means one hold value must depends on both the clock period T and the number of bits N. The time for one analog to digital, one analog to digital conversion, one analog to digital conversion must depends on both the clocks period, both the clock period T and the number of bits N, the number of bits N. Therefore, conversion time, TC is the conversion time, is equal to the number of bits N plus 1 into T. Where TC is the conversion time. Where TC is the conversion time. T is the clock period. T is the clock period. N is number of bits. Number of digital data. That means output bits. One clock pulse is required for SAR to complete compare each bit. However, an additional clock pulse is usually required to reset the register prior to performing conversion. That means here we use +1. Next one clock pulse. One clock pulse is required. One clock pulse is required for SAR to compare each bit. And an additional clock pulse and an additional clock pulse. The additional clock pulse is usually required to reset the SAR, prior to performing conversion. For n bit converter, the number of pulses required is n. For n bit converter, the number of clock pulses required is is n. These are some important points related to successive approximation analog to digital converter. Example. First one, Vin is equal to 212. Vin is 212. This is one hold value. One hold value. One hold value. At the start of conversion cycle, the SAR is reset by hold the start signal, that is high. First here is at the start of conversion cycle. At the start of conversion cycle, the SAR, successive approximation register, is reset by holding the start signal. S is high. By holding the start signal is high. That means the bits of that SAR, 8-bit of that SAR is reset. That means Q7, Q6, Q5, Q4, 3, 2, 1, and 0. All bits are zeros. Start signal is high means the SAR is reset. The SAR is reset. Okay, next point here is for 8 bits, 8 clock pulses will required. For the first clock pulse, the transition is from low to high. The transition is from low to high. That first conversion, MSB, this one is MSB. This one is LSB. The MSB bit is set to 1. All are zeros. All are zeros. This one is MSB. This is 1, 2, 4, 8, 16, 32, 64, and 128. This is the 128 is VA. The total here is conversion is this is 28. This is 128. This 128 SAR for the conversion process, SAR changes the bits. That means Q7 is changed to 1. The comparator compares. This is the comparator. This one is plus, then V in is 212. This is VA. VA is 128. 128. That means V in is greater than VA. V in is connected to non-inverting terminal of the op-amp. VA is connected to inverting terminal of the op-amp. When V in is greater than VA, this is the comparator, one of the building block of that successive approximation analog to digital converter. The output is 1. The output is 1. The output is 1 means V in is greater than VA. See the Q7 bit is as it is, and Q6 bit is V in is greater than VA. The output of the comparator is 1. Q7 is 1. The next bit of that Q7 is Q6 is also 1. The remaining Q5 to Q0 all are zeros. All are zeros. All are zeros. This is the VA for the. This is the VA for the next clock cycle. This is the VA for the next clock cycle 2. This is 128 plus 64. 128 plus 64. That is 192. 192. For the next clock pulse 2, see the comparator. V in is 212. VA VA is here is 192. Again, Vin is greater than VA. Vin is greater than VA. The output of the comparator is 1. The output of the comparator is 1. The output of the comparator is 1 means here Q6 is MSB. Q6 is MSB. Q6 is as it is. And Q5 one is fixed one. Q7 that bit comparison is Q7 bit conversion is completed. Now concentrate on Q6. Therefore, new VA is equal to the SAR changes to new changes this data. Q7 is 1 as it is. Q6 is 1. Vn is greater than VA. And the next bit Q5 is also 1. Q5 is also 1. Q5 is also 1. The remaining Q4, Q3, Q2, Q1 and Q0 zeros. This one is 128, 64 and 32, 3 bits. 128, 64 and 32, that is 4. 224. This one is 224. For the third clock pulse, for the third clock transition, plus minus. This Vin is here 212. VA conversion digital to analog converter output is 224. Here VA is greater than Vn. VA is greater than Vn. The output of the comparator is 0 because VA is connected to negative inverting terminal of the op amp. Vn is connected to non-inverting terminal of the op amp. That is output of the comparator is 0. The new VA, the SIR changes that bits VA bit. Q7 completed. Q6 is also completed. Coming to Q5. Q5 is changed to 0. Q5 is changed to 0. That is Q4 is 1. Q4 is 1. Q4 is 1. If VA is greater than Vn, VA is greater than Vn, that particular bit Q5 is 0. Q4 is set. Q4 is set. Q3 to Q0 all are zeros. This one is 128, 64, 32, 16. This one is 16. 3, 9, 10. That is 208. 208. This one is 208. 208. For the next clock pulse, 4 here plus minus. Here Vn is 212. VA is 208. 208. VA is 208. That means Vn is greater than VA. Vn is greater than VA. Therefore, output of the comparator is 1. The SIR adjusts the bits VA. That is Q7, Q6, Q5, Q4, Q3, Q2, Q1 and Q0. 7, 1, 0. Here Q4 is 1. Q4 is as it is here. Q4 is 1. Q3 is also 1. Q3 is also 1. The remaining are zeros. The remaining are zeros. This one is 128, 64, 32 is absent, 16, 16 and 8. 16 and 8. 2, 10, 11, 2, 16. 2, 16. For the fifth clock pulse, plus and minus here, this is V in 212. This one is VA 216. VA is 216. VA is greater than VA. VA is greater than VA. The output of the comparator is 0. The output of the comparator is 0. Therefore, the new VA is equal to Q7, Q6, Q5, 4, 3, 2, 1, and 0. Here, concentrate on these 2 bits. The remaining are completed. 1, 1, 0, 1. Here output is 0 means 1 is replaced with 0. 1 is replaced with 0. And Q2, the next bit is 1. The remaining are zeros. The remaining are zeros. 1, 1, 1, 1, 0, 1, 0, 1, 00. This one is 1, 2, 4, 8, 16, 32, 64, 128. 64, 16 and 4. The ప్రతిపక్కన 12. ఆరు 9, 10. 202. 128, 128, 64, 16, 8, 8 plus 4, 12, 12 plus 10, 12, 2, 2 to 4, 10, 212. This one is 212. This one is 212. Now we will concentrate on these 2 bits. Next 2 bits. Next 6th cycle. For this 6th cycle here, plus minus. This one is V in 212. VA is 212. For equal, some discrepancy is there. Choose the output of the comparator is 1. The output of the comparator is 1. Even this equal, some difference is there. Therefore, VA is equal to Q7, Q6, Q5, 4, 3, 2, 1, and 0. These are the 1, 1, 0, 0, 1, 0. That is 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, like that. For 7th cycle, come find out this one. Find out this one. 128, 64, 16, 64, 16, 4, and 2. 4 and 2. 18, 24, 4, 2 to 10, and 214. This one is 214. For seventh cycle, clock cycle, V in is 212, VA is 214. VA is greater than VN. Output of the comparator is 0. The output of the comparator is 0. Therefore, compare these two. So the SAR adjust the bits 6, Q5, Q4, Q3, 0. This one is 1, 1, 0, 1, 1. This one is changes to 0. Find out this one. Before 32 is absent. Next one is 16, 8, 8, 4, 1, 4, 1. 19, 20, 21, 22. 10, 11, 2, 1, 5. Ten, 18, 21, 22, 23, 4, 10, 11. For the eighth cycle, this one is VN is 212, VA is 230, VA is greater than VN. The output of the comparator is 0. Therefore, new VA is equal to Q7, Q6, Q3, Q2, Q1, and Q. This one is 1, 1, 0, 1. Here Q1 is same. Q2 is Q0 is 0. Q0 is 0. Convert this after 8 cycle. This is 2, 4, 8, 16, 32, 64, 128. 128, 64, 16, 16, and 4. 6 plus 4, 10, 18, 22. 2 to 4, 4 plus 6, 10, 11, 12. Therefore, VA after 8 cycles, VA is equal to VN. VA is equal to VN. Therefore, the hold value 212 is converted into digital data. The digital data is 0, 101, 1101, 1, 2, 3, 4, 5, 6, 7, 1, 1, 1, 1, 1, 0, 101, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. This is also 212. This is also 212. After 8 clock pulses, the conversion has been completed. The advantage of successive approximation analog to digital converter is its high speed and excellent resolution. The advantage of the successive approximation analog to digital converter is its high speed